All right, 4-1, 4-2, 4-3, force. I don't know if I'm going to do a video on 4-1 and 4-2 so much. Not 4-1 for sure, I think. But I will. I might come back to that later on about proportional relationships and things like that are here. But mainly 4-3. But I'll talk about 4-2. So I should have put 4-2, 4-3. Or I didn't know I had my color printer on. I was going to print these out. Wow, I have some scientists there for you. I'll tell you about them in the Zoom or in class as well. But this chapter we're going to be doing is on force. And this is really where physics began. It was with Galileo, and then really soon after that, like in the same time as his lifetime, Newton. Newton got all this information, contemporary, that just did it. It's incredible what was done. Well, anyway, there's a little thing you can read on there about the differences in opinion for Aristotle and Galileo early on about what forces were. Well, it's interesting. I guess I'm going to say a little bit about it. Let's just say I take an object. Well, I just have this on a string. I just happen to have it. Well, just say this is from a ratchet set, like a heavy piece of like a tool. If I take this piece and say you throw it, okay. Well, actually, I could do that, couldn't I? With a string, I could be safe. But say I throw it across, or like let it move across. I move it. Okay. Aristotle believed that when you threw an object, that there was a force that stayed acting on it as it moved, and that kind of and then the force ran out, something like that. Like it was constantly getting a force pushing on it. Well, Galileo showed that this wasn't true. Actually, I don't know the best. I don't have the example. It's on the paper what he did there, but I'm just going to go and jump ahead to Newton's law of motion. Newton, and you can say that Galileo is also credited with this. So I really think Galileo did it, yeah, and then Newton kind of went on with it and then expanded further. But the law of inertia, the first law of motion, let me see. Yeah, like I did write on the paper under Aristotle, and I'm not going to ask you about this, but Aristotle believed an object can only move as long as a force is being applied to it. So what that means, you throw a baseball, as long as you're putting a force on it, it will continue to move. Now that makes sense in some ways. Like if you have a big box or a refrigerator, how about a refrigerator? You're trying to move a refrigerator across the floor, you're pushing it, or pushing a heavy filing cabinet across the floor. As long as you're pushing, it moves. You stop pushing, it stops moving. Well, that's because of friction. But now, when you throw a ball, that's not the case. You think, wait a minute, am I still applying a force every moment as it moves? Well, Aristotle believed it was. Galileo proved that was not true in the law of inertia. So the law of motion, the first law of motion is called the law of inertia. And what that tells us, inertia means resistance to change in motion. I should say that. The resistance to change in motion. Here's another way you probably heard it said before. An object that is moving. Or how about this? An object will stay in its same state of motion until or unless a net force acts on it. Okay, so an object will continue to stay in its same state of motion until or unless a net force acts on it. Okay, so here's what it means. When I throw this ratchet piece, all right, when I throw that, it will continue to move. I won't actually throw it across the room like that. It will continue to move in a straight line at the same speed unless or until a force acts on it. Now, it's amazing. This is true. This is true, but it's amazing that Newton was able to figure this out, because he didn't know about, he was not able to travel to other planets or the moon where there's no air or when there's less gravity. Okay, because when you throw a ball in the air, two things happen. You know, does that ball continue to go forever? Or how about a basketball? You throw a basketball across? No. We know that what we see that happening is as the time goes by, it's going to come and it's going to hit the bottom. I mean, maybe it'll go through the hoop first or whatever. The ball's not going to continue to move. Now, if you were in outer space, away from any gravity, no air, it's true that object will continue to move at the same direction, at the same speed, infinitely until a force acts on it. Well, the basketball that was thrown here, a force is acting on it. Actually, two. One would be the air. Air resistance is slowing it down a little bit. We always ignored that, but for a basketball, it's a little bit more significant. For a beach ball, like a blow-up inflatable, it would really be significant. Try to throw a beach ball and it's going to slow down really easily. But so you have the air resistance, but even more important, you have gravity pulling it down. Okay? So otherwise, it will continue in the same state of motion, but it doesn't because of that, because of the air resistance force and because of gravity pulling it down. Force, by the way, is any push or pull on an object. And you can say we can measure the amount of push or pull in pounds, or in the in our class in physics in metric system, pound is the English unit, but the one we're going to use is called Newton. Actually, it's capital N, Newton. I'm going to show you that in a moment. I'm going to do a calculation. So first law of motion just is the law of inertia that says an object will stay in its same state of motion. So when I say, the reason I like to say it that way, if an object is at rest, and I mean at rest relative to us, like right now, I'll just put it in my hand. This object is not moving. It's going to stay at rest until a force acts on it. Now, if I move my hand, watch me do this quick. Well, I moved it right there. Okay, it moved up a little bit. But if I do that, up, boom, look at what happened. So a force, gravity, pulled on it when I moved my hand over. So it would have stayed in its same state of motion, except a force acted on it. It was being blocked. You could also say that my hand, and it is true, is resisting the force acting on it of gravity. I'm canceling it out right now, but my hand gets tired or I move the hand, well then boom, you see that a force will act on that object. And the amount of motion, actually that's going to be law number 2. So law number 1 is the law of inertia. It's kind of, I know it's more of the boring one. I guess it's more fun in class. I can throw something and show you better. The second law of motion is in 4.3. And actually the second law of motion, now this is Newton. Newton figured out something even more amazing. And you'd already know this too. So let's just say that I go and I've talked about this before. Okay, I've talked about it before. But let's just say that you had, well, it'd be really hard to do this, but I'll bring it anyway. If you ever had a car that ran out of gas or something was wrong, you had to push it to roll it. Well, let's say you had one of those little smart cars, little smart car. Oh, smart car breaks down on the freeway. Well, not on the freeway, they can't go there, I think. But those stupid little smart car stops in the middle of a busy road and it's messed up. Okay, actually, I guess you could kind of just push it over to the side and just in the lane you can still go around it. But forget that. But that little smart car. If I go and let's just say I'm gonna get like a, well, let me see. I don't know what we can use. I guess it was an animal, like an elephant or something. If you get an elephant to pull that thing with all of its force, boom, that elephant pulls that little smart car. It just takes that thing off. That thing's bouncing around, the smart car behind it. So you pull it on, you tie it to an elephant. You get that elephant starts to charge. Okay, what if you take that same elephant, and now you tie it to, I was going to say an 18-wheeler truck, but I don't know if the elephant can pull it. But maybe if all the brakes are off and everything. So now, let's do that. Tie it to a giant 18-wheeler truck. Let's say that elephant has the same, energy, force. It's pulling the same. Is it going to be able to speed that 18-wheeler up the same way that it sped up the smart car? No, not at all. Now, you'd know that. So a light object, I could actually show you this and try it. I know I make it so abstract. I don't know how to do it on the video, but I even what I just had a moment ago. Where did I throw my little string there? Where is it? Well, okay, here it is. Here it is right there. like, okay, so if I want to accelerate this, if I pull this with all my force, think about how much I can get that thing to move. Well, instead, if I tie it onto it, like here's a little plastic pin. If I were to pull this pin instead with the same force, look at what I can do. I can just really shoot that thing around. You know why? Because this has a very low mass. So if I'm putting the same amount of force onto that little pin, swinging it around, okay? The same force, if I put the same force on the metal piece, oh, that didn't feel too good. I kind of hit myself. I'm not able to get as much when I put the same force on it, same force on that, same force on this. Well, you can't really tell too much. But obviously, you're going to be able to speed this thing up a whole lot more because this has less mass, it has less inertia. I didn't mention this earlier, but mass measures inertia. So the more mass you have, the more resistance you have. It's very hard to push the 18-wheeler to get it to move because it has a lot of mass, a lot of inertia. But if it's easy to push a smart car, a little small or a little toy car, a wagon, because it has very low mass, low inertia. So the second law of motion is actually an equation that Newton gave. Groundbreaking, amazing equation. And you've all seen the equation E equals mc squared. You've seen that everywhere. Like Einstein, you think, oh, how smart, how incredible that was. Well, this was probably even more influential and groundbreaking in our science today. F equals ma. The net force on an object is equal to its mass times its acceleration. So let me do a couple of problems in here, and I think you'll find this pretty easy. I'm going to say more about this because we're going to talk about this in lesson 4.4. I'm going to say more about net force, but I'm just going to show you the easy kind of calculation stuff for the beginning of this. And the Newton's second law of motion just says this: the acceleration of a body is directly proportional to the net force acting on it, indirectly proportional to its mass. The direction of acceleration is in the direction of the applied force. I'll explain that as it goes. Okay, so letter A, the problem it says, Happy throws a 15-kilogram stone, accelerating it at a rate of 4.25 meter per second squared. It's right here on the paper. Okay, net force does Happy put on the stone? Okay, this is an easy little plug and chug thing. Just use the equation, and we say it's a 15-kilogram stone. That's actually 30. That's pretty heavy, like a 30-pound. So you're going to take that thing and I don't think it'll just throw it. It says accelerate it, so maybe he swung it like that. All right. I guess a little bit heavier than a bowling ball. So think about a bowling ball. That's about how much that would be. But I guess you could have a bowling ball that's around 30, 35 pounds. But I think usually it's a little bit lighter, isn't it, for most people? Depends on how strong, how big you are. Okay, so 15-kilogram stone, acceleration is 4.25 meter per second squared. So we multiply those out, 15 times 4.25, and it's 63.8. Now, the unit would look like kilogram. Then you see that came from the mass, and from the acceleration, it's meter per second squared. Well, maybe it was Newton, or I don't know, but I don't think it was Newton. Someone decided, let's just take all three of those letters when you have kilograms, or if we want to say kilogram meter over a second, and let's just turn that into the letter N, meaning Newton. 63.8 newtons. Now, just as a side note thing, and it might come up on one of the problems later on, that 1 pound in the English system is 4.45 newtons. So really, it's about 4 newtons. What does that mean? A newton is about a quarter pound. So you think, what is something that weighs a quarter pound? And everybody always says, quarter pounder, McDonald's. Okay, so, but probably In-N-Out burger is also probably about a quarter pound of beef. So if you think about that, if you hold like a quarter pounder, that is about 1 newton. So if you had 4 quarter pounders, well, yeah, that would be a pound, all right? 4 newtons is about, not exact, I mean, it's 4.40, but close. Okay, that's pretty easy to calculate this first one, I think. All right. Now, this next one, this combines a little bit from last semester. And, well, I say last semester, but, it depends on when we are. But as I'm making this video, we didn't do this lesson. And so you have to use the kinematics equations. Like, what? Yeah, so they come back again. I like that one. Remember this one. This is actually the first one I always go for. Pretty much just these. I don't think you're going to see the other two, but these three are probably the main ones you're going to see. But it says on B, Rip pushes a cart, accelerating it from 2 meters per second to 11 over a distance of 14 meters. Calculate the net force that he exerts on the cart. And, okay. Now, one thing we also talk about in physics, it's always good to draw a diagram or a picture. Well, we don't really have to on this one, but, you can just imagine it's accelerated, and the distance it accelerates is, what do we say, 14 meters. So I guess I should put 14 meters behind it, actually. Yeah, let's put that. So we moved it over a distance of 14 meters, or just 14 meters, no O. And it says it went from 2 to 11. So maybe it was already rolling 2 meters per second and somebody ran it behind it, and now they've brought it up to 11. So this is not really needed for a diagram. But we're going to do a lot of amazing diagrams in this chapter, but not this section. Probably starting in the very next lesson. Okay. And then you know that the cart weighs 25 kilograms. I guess it's kind of good just to see a diagram of something. So first, what is the force he put on it? So the net force will be the mass, 25 times acceleration. We don't know the acceleration, but from last semester's equations, kinematics, we can figure it out. Actually, from that one right there. Looks like it, right? From V final squared is V initial squared. Now, we're not going to see too much of this. We might see it in the first section for the first quiz, but it's not going to happen too much in the chapter. But the final is 11 meters per second. The initial is 2. I ought to put 2.0. Yeah, it is 2.0 actually, okay? Because otherwise it's sig figs. And, we don't really care as much about sig figs in physics. But within reason, we gotta do something with it. And the delta x is the change in position, or the distance. It went with 14 meters. I'll just put 14. Well, I'll put meters. All right. Now, okay, so 11 times 11, 121. 2 times 2 is 4. And then that's going to be 28a. So 121 equals 4 plus 28a. So subtract 4 from both sides. So 121 minus 4 is 117. Is 28a. Then divide both of those by 28. And so a equals 117 over 28. 4.17. Well, actually, I only had 2 sig figs there, so I'll just put 4.2 is the acceleration. 4.2 meters per second squared. Now, one more thing the law says, and don't worry about all the long words. I'm going to be teaching the second law in this lesson and in the next lesson. In the next one, it's really going to make more, you'll understand a little bit better. But if I push this force, so I'm pushing with a force right here. We don't know the force. I'm pushing a force over 14 meters. I'm making it speed up from 2 to 11. Okay, and it's 25 kilogram. Okay, I'm pushing it in this direction. We'll just call that east. Well, it's also going to accelerate east. And that makes sense. The direction of the acceleration will equal the direction of the force that you're putting on it. So, anyway, we're not done with it yet. Oh, could you see the answer there? 4.2, sorry, is acceleration. So now F equals ma. I'll just put it over here on this side. I would use these 3 equations probably on the homework worksheet today. I'm just going to do this one problem only. But force is going to be equal to the mass, 25 kilograms, times 4.2 meters per second squared. So 25 times 4.2 is 105, sorry. Well, yeah, I'll just go with 105. I mean, if you put 110, but 105 newtons. So that's the force they put on the car in order to accelerate it. So it's a pretty easy equation. You can do C. On C, the only difference is we give you the force, and then we say find the final velocity of the car. So it's kind of like you're doing it backwards. For C, you'll know the force, and first you'll find out what the acceleration is. Then you go back over here, plug in the acceleration, and you got to find out the final. So I'm not going to do that. Maybe I'm going to do that in the Zoom lesson class for you. But all right, so on the worksheet, do number 1, 2, 4, and 5 on the worksheet. 1 and 2 are quite simple. Only 4 and 5 will use some of these equations over here. And that's not the biggest focus. The kinematics is not the biggest focus on this, but there, you'll see it in this first section. It's not the biggest focus of this chapter. We're going to do things much more beyond that. I'll see you guys.